But there is one trick that we can use to turn this into a single operation. And that trick is referred to as the use of homogeneous coordinates. If we write PB as its component along x, its component along y, just as we've done so far, and we add a third component. We add a 1 at the end. Okay? Now, I can combine my rotation and my translation into a single matrix operation. So if I write a matrix, a transform matrix that transforms from A to B as being the rotation from A to B, the translation vector from A to B, 0, 1, okay. So let's spell this out. Point P in A, which I also have to write in homogeneous coordinates. So I'm going to have Px, Py, and a 1 at the bottom. So let's spell out this matrix. We have the rotation part from A to B. This one is 2 by 2. Then we have Tx and Ty, which is the translation part. And then I have 0, 1. And this gets multiplied by PBx, PBy, 1, also in homogeneous coordinates. Okay? So if you carry out the multiplication, what you get is the rotation from A to B times Pxb, Pyb, plus the vector Tx, Ty, and then a 1 at the bottom, and all of this in matrix form. Which is what we were looking for. So, to recap, homogeneous coordinates. You can think of homogeneous coordinates as simply the trick of adding a 1 at the bottom of the column vector, which denotes a position in space. In robotics, this additional coordinate that we put here is always 1. In other fields, like computer graphics, there are reasons to make this something other than 1. But in robotics, this is always a 1. Why do we need it? Well, if we use it like this, we can afford to write transform matrices in this form. Then we can have the same relationship hold. PA is the transform from A to B times PB. Okay. Transform matrices are really, really important. This is the key to doing any operation in 3D space in robotics, and they always have this form. The top left submatrix is a rotation matrix. The top right vector is the translation vector. There is a 1 in the bottom right. The bottom left is all zeros. Again, for example, in computer graphics, you have reasons to make this something other than 0, to make this something other than 1. In robotics, always you look at the matrix. If it's a transform matrix, it has zeros on the bottom left, a 1 in the bottom right, a rotation part here, a translation part here. Let's do a concrete example. So this is our coordinate frame A. And then coordinate frame B let's say that the transform from A to B is the first question, is this a valid transform matrix? We inspect it. We look for the telltale structure. It has zeros on the bottom left. It has a 1 in the bottom right. The top left is a valid rotation matrix because it's orthonormal. The top right is always fine because any vector can be a translation vector. So yes, this is a legal transform matrix. What does coordinate frame B look like? Well, we look first at the translation part. So to get to the origin of B, we have to move by 2 units along x by 2 units along y. So then this is the origin of B. The axis of B, we look at the column vectors of the rotation matrix, and we see that this is xb, and this is yb. Okay? Now, let's transform a couple of points. So let's look at two points along somewhat in coordinate frame B. First, let's say that PB is 1, 0. So this is our point P. Okay. That same point in coordinate frame A is going to be the transform from A to B times the point in coordinate frame B. So we need to multiply these two. We cannot do it yet. What's the problem? We forgot the homogeneous coordinate for B. So let's quickly fix that. Okay. And I will try not to make the mistake again. I don't promise I'll succeed. That immediately tells you, though, the matrix dimensions didn't line up. Something was wrong. And what was wrong is that we had forgotten the homogeneous coordinate for PB. From this point on in the course, we should always, always, always remember the homogeneous coordinate. Now we can carry out this matrix multiplication. And what we get is 0.7 plus 2 0.7 plus 2 and 1, which gives us 2.7, 2.7, 1. Let's check this. First of all, the homogeneous coordinate should be 1. If we've made no mistakes, then we should always end up with 1 as the homogeneous coordinate. Then the actual coordinates of PA, 2.7, 2.7. So this is point P in coordinate frame A. And that is what we were expecting. Now, let's look at a different P. Let's say that PB is 0, 2. Always remember the homogeneous coordinate. So if we go 2 units along the y-axis, this is our point P now. And if we carry out the multiplication, we're going to get negative 1.4 plus 2 and 1.4 plus 2. So 0.6, 3.4, 1. we got the 1, that is correct. And then 0.6, 3.4, those are the coordinates of P in A, which by inspection looks right.